In this video, we'll be talking about general graphs and their equations. So, some very specific general graphs that we might play with eventually is a constant function. A constant function will look something like this. Now, you'll notice in these graphs, I'm going to leave off the arrows on the end of the axes, so it's clear what graph we're looking at. Now, the equation of this graph is going to be generally y equals some form of c. Again, y equals a number, a constant. So, an example of this might be y equals 2, y equals a negative 7, heck, y equals pi even would work. The next graph that we talk about is a linear graph. Linear graph looks something like this. Okay, it passes through the origin on a generic case, but it can pass anywhere along both x and y axes. The general equation for this is y equals ax plus b. Sometimes you'll notice it as mx plus b is what we've seen in the past, but this is the general equation. In the next equation, we'd have a quadratic. And a quadratic, again, its standard form looks like this. It is going to be generally ax squared plus bx plus c. At this point, we start talking about a very special format. So back in here, for the linear, again, this is constant, this is linear, this is quadratic. The linear equation has a format that looks like this, such that x1 comma y1 is going to be a very specific point somewhere on that curve, and m is the slope. Over here, we change this one to be y equals a x minus h squared plus k. So this first equation up here is going to be called general form. This equation down here is usually called standard form. The next equation we're going to talk about is the cubic. Now the cubic looks something like this in its general form. This is again a cubic. That's y equals ax cubed plus bx squared plus cx plus d. In its standard form, it would be a and then x minus h cubed plus k. Now this is not the only form of a cubic that we could see. For instance, we could see a cubic that looks something like this. It could also look something like this. It can't be sideways, however. That is not a cubic. So these are all different versions of a cubic that you might be able to see. They're going to either have an equation that looks like this or an equation that looks like this. After we've gotten through those ones, we would then move on to the next graph, and the next graph would be something called a polynomial. Now, it's important to note that a polynomial is actually every curve that we've already talked about. It just is referred to as a polynomial because it has a higher power than 3, and we don't want to give it a specific name. Now, this one does actually have a specific name called a quartic, but again, any function that is a linear power, a constant, a quadratic, or a cubic can also be referred to as a polynomial, but when asked what they are, you're going to want to refer to them specifically as one of those four. For a polynomial, however, again, it's simply y equals ax to the n. I don't know necessarily what n is. I can determine it, but that's going to take a little bit more work. Plus bx to the n minus 1, plus so on and so forth as we go down until you hit that constant value. There is no real generic form for this. We could just rewrite it again as ax minus h to the power of n plus k, but things get a little bit different in terms of the graph and how it's going to appear. But that's the concept of what a polynomial is. Now, after we've gotten past a polynomial, all other curves are going to be some semblance of a generic other curve. So, if we start with an absolute value equation will look something like this. It'll look like a V. What's important to note about an absolute value equation is that if you were to look at the linear, everywhere it's negative on the graph in terms of a y value being negative, all of those values just get flipped up here. So you'll notice all the values that would have been down here are now up here. So the absolute value is nothing more than a manipulation of a linear curve. Now, the absolute value could be a manipulation of a quadratic, a cubic, or any other function, but the absolute value specifically monitors what the function is, takes all the negative values in terms of negative y, and it flips it up. So this generic equation is going to look like this in terms of a standard form. A absolute value of x minus h plus k. Now, hopefully at this point you're starting to see a pattern here. y equals some value a times x minus h squared plus k, y equals some value a times x minus h to the power of 3 plus k, and then y equals a, absolute value of x minus h plus k. You'll notice that we have a function around x minus h, where a, h, and k are all very specific numbers, and there's squared, cubic, absolute value. Next function we're going to talk about is going to be the square root. The square root function is actually going to look like this. We did it in a previous video. Looks something like this. It is one of the only functions that abruptly just ends somewhere. This square root function has a generic form of y equals a, the square root of x minus h plus k. Looks familiar, again, doing the exact same information as all the other ones. This you'll also notice if you were to look at this curve up here and reflect it over a line y equals x. Then this thing here is flipped up, and this thing here is flipped down, and it's facing this way now, which is actually half of this square root function. You'll notice, if I put a dotted line here, that is a square root function right there, but it is not this square root function. Because of the function denomination on this, we must assume that this is a separate function from this, because otherwise it won't pass the vertical line test. So technically, you can see that a is a positive number, and that's this one. You could see a as a negative number, and that's this dotted line down here. But again, keep in mind, a square root function is only one half of this, where it abruptly ends at a very specific point. The next one is going to be a cube root. And a cube root function, if you think about it, is nothing more than this graph reflected again over that dotted line y equals x. So it's going to look something similar to this. And if you think about it, this is a square root, sorry, not a square root, a cube root of x minus h plus k, just like all the other versions. Again, the standard form is extremely important, so you'll notice here, 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 it's all going to be consistently used as the same functions. Even in the more complicated versions of these graphs, we start to end up using it there as well. What's important about all of these graphs and that h comma k point, either the vertex or the inflection point is going to sit at that point h comma k. In each of these graphs, this right here is h comma k, this right here is h comma k, this right here is h comma k. Polynomials are relatively difficult to identify that h comma k. Here's the h comma k, here's the h comma k. So all of these points allow us to do something with these graphs quite effectively later on. It's just important for us to note what these equations are going to look like all the way through.